Welcome back to another video. In this one we're going to talk about the inverse trigonometric functions. And in this video we're going to work through the proofs of sine inverse derivative, cosine inverse derivative, and tan inverse derivative. What we're not going to do is worry about any restrictions on the domain of those. Not sure what I mean? Don't worry about it. If you do know what I mean, then don't expect to see that as part of this proof. We're just going to do it assuming any value is fine. We'll start with y equals sine inverse of x. And we need to find the derivative. Well, we don't know what the derivative of the inverse sine function is. We do, however, know the derivative of the sine function. So somehow we need to change this so it has sine, not inverse sine. And the way to do that is to take the sine of each side. So we get sine of y on the left is going to equal to the sine of the sine inverse of x on the right. Now when you do that, sine and sine inverse are inverses, which means, for lack of a better word, they cancel, and we're left with the sine of y is equal to x. The derivative of sine of y we can do now. We do know what the derivative of sine is, so we can start taking the derivative here. The derivative of sine is cosine of y. But remember, y is a function of x, so that needs to be multiplied by the derivative of y, which we'll write as dy by dx. So that's the chain rule, or implicit differentiation, however you want to think about it. And the derivative of x is 1. So we've taken the derivative of each side. If you want to write that, we've taken the derivative of this side and the derivative with respect to x of that side. And this is the result. We're trying to find dy by dx, so we'll solve here for dy by dx. Gives us 1 over the cosine of y. But we don't want the derivative of y with respect to x to be expressed in terms of y, so we need to get rid of this y. And in order to do that, the first thing we're going to do is say, well, we know that the cosine squared of y plus the sine squared of y is always equal to 1. That's an identity that we know is always true, which means we can solve for the cosine of y and get the square root of 1 minus sine squared of y. That's just solving that identity. If we substitute that in, we get the square root of 1 minus sine squared y. And we still have the derivative of y in terms of y. If we just look back at our steps here, let me highlight it for you. Look at that step. Look what we had right there. Let's just write it again to the side here. This was sine y equal to x before we stuck in the other pieces. So that's what that said, sine y equals x. Well, we have sine y here, so we can replace that. Dy by dx is equal to 1 minus square root of 1 minus, instead of sine y, we're going to write x, so that's x squared. And there's your rule. So the derivative of y equals sine inverse of x is 1 over 1 minus x squared, all under a square root. So that's our first rule. Let's do an example of that. So the first example we can look at, let's say if we had y equals the sine inverse of 2x cubed. Well, the derivative then, y prime, the derivative of sine inverse is here, so that's 1 over the root of 1 minus whatever is here squared. So in this case it was the x, in this case it's 2x cubed. And then that has to be multiplied by the derivative of this part here, which didn't change, and that's the chain rule. So the derivative of 2x cubed is 6x squared. So that's using that rule. Let's go ahead now and see what happens for cosine inverse. So if we have y equals the cosine inverse of x, and I'm going to go a little faster through this one. Cosine of both sides gives us cosine of y equals x. Derivative of both sides, derivative of cosine minus sine of y multiplied by the derivative of y. And this time I'm going to just write y prime. And that's going to equal the derivative of x, which is 1. Solve for y prime. We get negative 1 over sine y. Sine y, we can use the same substitution as last time, except this time it's 1 minus cosine squared. And again, same as before, cosine y is x, so we can replace cosine y with x. And we finish the proof, which says the derivative of cosine inverse is negative 1 over root 1 minus x squared. And so there's your next rule. The derivative of cosine inverse is here. So let's try another short example of that one. Let's say f of x is equal to cosine inverse of x minus 3x squared, perhaps. F prime of x, then, the derivative, negative 1 over the square root of 1 minus the argument, or the part that comes after the inverse trig function, stays the same, and it's all squared. And that gets multiplied by the derivative of that, which is 1 minus 6x. Well, that's our second inverse trig function. Let's try to do the third then. And it'll be similar, only with a different identity. So if y is tan inverse of x, or let's try, instead of tan inverse of x this time, let's do tan inverse of u, where u is some function of x, just to write it using the chain rule. Tan of both sides, we get tan of y is equal to u. Derivative of both sides, and this is the only real difference for this one. Derivative of tan is secant squared y multiplied by the derivative of y, and that's going to equal the derivative of u, which is u prime, or written a different way, du by dx. Solving then for the derivative, y prime is equal to, I'm just going to leave the 1 up top, secant squared y multiplied by this part, which is the derivative of u with respect to x. Secant squared, well, just like we had the identity sine squared plus cosine squared, we also have the identity secant squared of x is equal to tan squared of x plus 1. Another identity you should be familiar with. So we replace secant squared y using this identity. We end up with 1 over tan squared y plus 1 times du by dx. So if we finish simplifying, then we get 1 over, well, tan y is just u from up here, so we end up with u squared plus 1 multiplied by the derivative of u with respect to x. And that's just the chain rule. So let me just write that here for you without the chain rule. If we had done it just with x, would have looked the same, except it would have been 1 over x squared plus 1, and that's it. So that's the rule to remember. This is the same rule, except with some function of x here, so we have to use the chain rule. Quick example, let's say y is equal to the tan inverse of, and let's stick a different trig function in there, let's say of the cosecant of x. So the derivative then, well, tan inverse is 1 over cosecant squared x plus 1 now. The argument comes down, becomes squared plus 1. You can see it in either of the rules. Multiplied by the derivative of the argument. So the derivative of cosecant of x is negative cosecant x times cotan x times the derivative of x, but that's just 1, so we don't have to worry about that. And that's the derivative. We won't worry about any simplification. Let's just make sure we can get the derivative part, and we can worry about the simplification in another video. So that's your 3 inverse trig derivatives. In the next video, we'll look at some more examples so you can practice applying the rules.